When we first talked about multiplication, we said that multiplication could be viewed as repeated addition. In fact, we had an example like this. We had the repeated addition of some number, and I'm using 3 here, and notice that 3 is used as an addend 4 times. So we can think of this as 4 times 3, or 3 times 4. Now, in a similar way, we have kind of a shortcut. We can think of multiplication, you see, as a shortcut of repeated addition. We also have a shortcut in mathematics for repeated multiplication of the same factor. Now, notice that 3 is used as a factor here 4 times. And to consolidate that idea, or the mathematical notation for that idea, is to write this 3 and then write a little raised 4. You see, a little small raised 4 to the upper right of this number. And 4 indicates the number of times that this number is used as a factor. So we have 4 factors of 3. 4 is called the exponent on 3. Now 4 is an exponent. So 4 is called an exponent, and the 3 is called the base of that exponent. So, base exponent. The exponent tells us how many times the base is used as a factor. And in some circumstances, we work problems involving bases and exponents in this direction. You see, we have repeated factors and we show them or consolidate them using an exponent notation. And other times, we have a base exponent arrangement and we need to show the separate factors. So let's go over all of those situations. But let's make sure we understand this idea first, where we have repeated factors of the same kind and we use an exponent to illustrate what we have. Here we see that we have 1, 2, 3, 4 factors of 5. So that is 5 to an exponent of 4. 5 is the base. 4 is the exponent. It tells us we have 4 factors of 5. We read this as 5 to the 4th power. 5 to the 4th power. Here's another. 7 times 7. Notice that we have 2 factors of 7. So 7 is used as a factor 2 times. This is 7 to the 2nd power. Now there's another way to say this. An exponent of 2 has a little nickname. It's called squared. We can think of it as a nickname. There are some other compelling reasons for using the word squared. But for right now, we can just call this 7 squared. Seven squared, or 7 to the 2nd power, is just fine. Here's another one where there's a little nickname involved. Notice that we have 6 used as a factor 3 times. So the base is going to be 6, and the exponent is going to be, well, 1, 2, 3. So 6 to the 3rd power is a way to read this. Or we could read it as 6 cubed. So an exponent of 3 is read as cubed, and an exponent of 2 is read as squared. So this is 6 cubed as a way to say this. Here's one involving repeated factors of 2 different kinds. Notice that we have 2 factors of 6 and we have 3 factors of 4. And we can indicate that using exponents like this. We have, let's see, the base would be 6 and the exponent 2, or squared. So we have 6 squared here, times base of 4 and an exponent of 3, because we have 3 factors of 4. So we say this is 6 squared times 4 cubed. Now 10 is a rather interesting situation because of just kind of the natural way that the zeros occur when we multiply tens and all that kind of thing. Let me show you what I'm talking about. I have here 4 factors of 10. All right, so in exponential notation, it would be a base of 10 and an exponent of 4. Now notice this, that I have 1, 2, 3, 4 zeros here. 4 zeros here. And I have a 4 as this exponent. That's not the most important thing. Notice this, that if I multiply this out, if I have 10 times 10, that would be 100. 100 times 10 would be 1,000. And 1,000 times 10 would be 10,000. So the number 10,000 is the number that we get if we multiply all of this out. Notice the number of zeros we have here. and notice the exponent 4? You see, that's kind of handy. And this situation goes both ways. If we have 10 to the 4th, then we have a number which is a 1 followed by 4 zeros. You see, and so we can immediately find that number without even going through this process of multiplication. Now, and the situation works the other way as well. If we have a 1 followed by 4 zeros, we know that we're going to have 10 to the 4th power. The 4 corresponding with the number of zeros that we have. So it's real quick. We can very quickly describe the number 1,000 in terms of 10 to some exponent. It is 10 to an exponent of 1, 2, 3, 10 cubed. And after all, this says that we have 3 factors of 10. 10 times 10 times 10, oh, that's 1,000. And for a million, no problem. It's 10 to an exponent corresponding with the number of zeros we see. We see 6 zeros. The exponent on 10 is 6. Now, let's kind of go in the other direction. We've been taking many factors and we've been kind of consolidating the expression by using exponents. Now we see some expressions involving exponents and we'd like to expand them. We'd like to actually multiply them out. Now, 7 squared means we have 2 factors of 7. And I'd like to write the factors down and then multiply them. So we have 7 times 7 for 7 squared. And then times 4 cubed means we have 3 factors of 4. So I'll write 4 as a factor 3 times. Now, 4 as a factor 3 times does not mean the same thing as 3 times 4. See, 3 times 4 is 12, but 4 times 4 times 4 certainly is not 12. You see, it's a completely different thing. The tendency when you first see exponents is that you want to multiply the exponent times the base. You see, but that is not what we need to do. All right, in order to evaluate this, we can multiply in any number of ways. You know, we have the commutative property of multiplication available to us, so we could change the order of things. We could multiply this 7 times that 4, this 7 times that 4, and then the result of those 2 times 4, and all of that kind of thing. But a kind of a safe way to do it is to do like this. 7 times 7 is 49, and then I can say 4 times 4 is 16. And 16 times 4, think about it, 64. And then multiply 49 times 64 to find 3,136. Whoops, 3,136 to be that product. Here's another one. Let me draw a line here for separation purposes. All right, we have 2 times 3 to the 4th power times 5 squared. So we have a 2 factor. We have 4 factors of 3. Now be careful in writing these down. And then we have 2 factors of 5. And now once again, we can multiply these numbers in any number of ways, but a very nice way to do it is like this. Just, let's see, the 2, and then 3 times 3 times 3 times 3. I can think of 3 times 3 is 9, 9 times 3 is 27, and 27 times 3 is something that I can't come up with real quick. All right, well, what I can do is I can kind of separate them in pairs. 3 times 3 is 9. This 3 times 3 is also 9. 9 times 9, oh, I can do that. That's 81. You see, and it turns out that 27 times 3 a minute ago is 81 as well. All right, let's see, 5 times 5, 25. And now, I can multiply any 2 first. It's pretty easy to multiply 2 times 25. That would be 50. And then 50 times 81. You see, when I multiply 50 times 81, I have this 0 sticking out there. Remember the shortcut with that? Let me show you. If you don't quite recall that, if I have 81 and I'm multiplying by 50, remember 0 times these will just give 0, and then 5 times 1, 5, and then 5 times 8, 40. So it's 4,050. So really it's just a 0 for that 0, and then 5 times the 81 for these digits. You see, that's the fast way to do it. So 4,050 is the number for this product. Here's one more. We have 2 factors of 5, we have 3 factors of 2, and we have 3 factors of 10. This is 5 squared times 2 cubed times 10 cubed is the way we might read this. Now, if we're going to list all of the factors, here's what we would do. It would be 5 times 5 times 2 cubed, 3 factors of 2, 2 times 2 times 2, and then 10 cubed is 3 factors of 10, 10 times 10 times 10. And now let's consolidate matters a little bit. We have 5 times 5, 25. We have 2 times 2, 4 times 2, 8. And we have 10 times 10 times 10. That's really easy. That's 1,000. All right, now we have a few ways to do this. We can do 25 times 8, and that's not too difficult. We could do 8 times 1,000 is 8,000. That's not too difficult either. And in fact, that looks so inviting, I think I'll do that. You see, 8 times 1,000 is 8,000. Now, 25 times 8,000, I have all these zeros sticking out, so I can just say that my answer is going to contain 3 zeros at the right, and then 8 times 5 is 40. I'll write the 0 and carry 4. 8 times 2, 16, and 4 is 20. So I have 200,000 for this product. If you were faced with this problem, 2 plus 3 times 4, how would you go about working this? It seems like we have a choice here. It seems like we could work it by adding the 2 and 3 first and then multiply by 4, or we could multiply 3 times 4 first and then add the 2. Well, let's work it both ways and see if it makes a difference. 2 plus 3 would be 5, and then 5 times 4 would be 20. Here's the same problem. Suppose we do it the other way. Suppose we multiply 3 times 4 to get 12, and then we add 2 and 12 to get 14. Well, there's a big difference between 20 and 14, so there must be a right way to do this. What are we going to do? Well, we agree in mathematics that when there is no clear direction as to how we go about performing operations in an expression like this, and we agree that there is an order associated with the operations, and we form an order of operations agreement. Do you agree to this agreement? Well, sure you do. Everybody does. And here's the agreement, the order of operations agreement. Number 1, we perform operations within parentheses first. You see, as the first order of business, it's like the parenthesis is just magnetizing us to that area of the problem. Well, I'll show you what I mean in just a minute. The next thing we do is raise bases to exponents. So we do parenthesis, what's inside parenthesis first, then we take care of the exponents, raising the bases to those exponents, and then we perform multiplication and division from left to right, and then we perform any additions and subtractions from left to right. Now, if we were using this order of operations to work the problem that we had over here, notice that multiplication and division takes precedence over addition and subtraction. So over here, if there aren't any other rules or guidelines to tell us what to do first, we see addition here and we see multiplication. And between those two, our order of operations says to multiply before we add. So we multiply these two rascals, and then we do the addition. And that's the correct way to work it. So 14 is the correct answer here. Now, to help us remember this order of operations agreement, the parenthesis over here is a P. The exponents is an E. The multiplication and division, the addition and subtraction. And it's please excuse my dear Aunt Sally is a good way to remember it. Please excuse my dear Aunt Sally. Parenthesis, exponents, multiplication, division, left to right for these, and addition and subtraction, left to right for these as well. All right, let's take some examples. We have in this problem, we see addition, we see subtraction, we see multiplication, but we see parenthesis. And parenthesis is the very first thing we do. So we ignore everything else in the problem, and our attention is drawn right here. You see, we're right into this part of the problem, and we ignore everything else. We're going to bring everything else down and just deal with this. So we'll write the 16, we'll write the plus sign. 8 minus 3 is 5, so we have 5. Now, I can leave the parenthesis here and bring down this times 2. Now, parenthesis, though, means do me first in a problem. It draws you to that part of the problem. But it also means to multiply. And you simplify what's inside parenthesis, and generally you multiply to get yourself out of it. You see, you multiply whatever's in the parenthesis times whatever is outside of it. So here, this is 5 times 2, and that multiplication is understood whether you have the dot here or not. That is, this can be written as simply 5 times 2 like this, or even if we drop the parenthesis and keep the dot, it would be 5 times 2. So any of those ways to write this would be okay. All right. So we have multiplication here. We have addition right here. Please excuse my dear Aunt Sally. Oh yes, we do the multiplication first. So it's 16 plus 10. And then 16 and 10, 26 for the final answer. In this next problem, we don't have parenthesis involved, but we do have exponents. And our order of operations says to raise bases to exponents before we perform other multiplications or additions. So from left to right, we're thinking 2 squared. That means 2 times 2. That's 4. We write that down. And 3 squared is 3 times 3, or 9. Notice the time sign, the little dot, is written between the 4 and the 9. We just brought that down from the previous step. And now we bring down the other part of the problem. And then again, referring to our order of operations, we're thinking, well, what do we do next? Well, we've taken care of the exponents, and now we take care of multiplication or division from left to right. Well, we see 2 indicated products, or 2 indicated multiplications here. So from left to right, we think 4 times 9, well, that's 36. We'll write that down. Then bring down the plus sign. And then 2 times 3 is 6. And now the next part of our order of operations would say, well, let's go ahead and add. We add from left to right, add or subtract from left to right. 36 and 6, 42 for the final answer. Here we have both parenthesis and an exponent involved. And remember, according to our order of operations agreement, we are drawn to this part of the problem. So we're just going to bring down all of these items. So we'll bring down the 2 squared and then the plus 3. And we do this operation first, the operation in parenthesis. So 6 minus 2 is 4. And now we multiply to get ourselves out of it, you see. Now, this is a multiplication problem now. We have taken care of, or we have simplified everything within the parenthesis. So now it's a multiplication problem, and we have this exponent situation. So if we're going to follow our order of operations agreement, parenthesis, then exponents, you see, inside parenthesis, and then exponents, and then multiplying and dividing, then we need to do this next. So we'll have 4 plus 3 times 4. And now the multiplication before the addition, so 4 plus 12, and then 4 and 12, 16. Now you may be asking yourself or thinking, well, gee, can't we do more than one operation at a time? And in some circumstances, it's okay. In some circumstances, it's going to come out all right. There were several items that could have been done in the same step, or several operations that could have been performed in the same step in this problem, and you would have gotten the correct answer. But by and large, overall, when there are choices, and particularly when those choices involve one another, if a parenthesis has an exponent outside of it, you see, do you raise to the exponent first, or do you do what's inside parenthesis? You do what's inside parenthesis, you see. And there are other many situations where the operations will have something to do with one another in a problem. And so it's very important to know the order of operations agreement for those situations.